All right, so you've had some time here to try to think this through. And we looked at this first one. If the derivative is 2x, you guys picked up really fast that the original function would have been x squared because the derivative of x squared is 2x. So as we look at these other examples, when you had f prime of x equals x, what did you say the original function was?
1/2 x squared.
A half x squared, okay? It's a half x squared. And the reason is because when I do the derivative of x squared, I get a 2x, but I wanted it to be a 1, so I have just a half x, and that half will cancel out the 2 when I take the derivative, okay? So for x squared, what was it?
X cubed over 3.
Yeah, 1/3 x cubed or x cubed over 3, okay? And again, that's because if I took the derivative of an x cubed, that would give me a 3x squared. So to get rid of the 3, I'm going to multiply by a 1/3. Okay? Now how about this x to the negative 2 power?
2 times x to the 1/2.
Negative 1 over x, what'd you say?
2 times x to 1/2.
Our first answer there was a little better. Negative 1 over x. Okay? So if you think about this, that is negative x to the negative 1 power, right? So negative x to the negative 1 power. Negative 1 times negative 1 is positive, so that's what makes it positive. But then you subtract 1 from the exponent, so now it's x to the negative 2. Okay? I will tell you this, the negative exponent ones, for some reason, are always trip people up. Alright, so just really be careful with these. When you have x to the negative 3rd power, negative 1/2 x to the negative 2. Okay, or negative 1 over x, 2x squared. Okay, we can again double check our answer. X to the negative 2, the derivative would be negative 2x to the negative 3. So I multiply it by a negative 1/2 to get rid of the negative 2. Okay? Thanks. Okay? And then finally, if you know the rule, what function's derivative equals cosine? Sine. Okay, so that's kind of a nice, easy one. All right, when you think about it. Okay, so there you go. All right, so we were thinking about derivatives throughout all of this. Okay, we're constantly thinking about derivatives. And that's because this whole thing is the antiderivative. Opposite of the derivative is what we're trying to do here. Okay? So, now, David, what did you say when we were talking back there? What did you ask Zoe and Evan?
His name's Drew.
Sorry, Drew. I don't know why. I keep mixing up David and Drew. I keep mixing you guys up. I don't know if it's the haircut or what, but.
What if you add?
Sorry.
What if you add just like +2 to the original function?
Okay, Drew. So. Jeez. It's only November, right? I think I have it figured out by now. Okay, so here's what he said. What if I add 2 to all of these? When I take the derivative, is that going to impact my derivative?
The same. Because the 2 goes away.
Yeah, because the derivative of a constant is 0. And that is exactly why what I told you earlier is true, and that is that the antiderivative is not exactly an inverse to the derivative. Okay? It's not exactly an inverse. So that we're going to look at down here. We're actually going to prove that you can add any constant to an antiderivative, and it will also be an antiderivative of that function. Okay? So, and that's where we'll get this plus C idea. But let's build up to that. All right, there's a couple of things that we need to make sure that we know. One is the term differential equation. All right, in a very, very basic definition, a differential equation is an equation that has a derivative in it. Okay? It has a derivative in it. So here's a very basic differential equation. Y prime equals 2. Okay? Y prime equals 2. And what we're going to do is we want to actually solve for y. So what we do is take the antiderivative of both sides. Okay? The antiderivative of y prime is y, and this is going to be 2x. Alright? But as we just talked about, it could be 2x or 2x plus 5 or 2x minus 7. It could be any of those. So what we have here is we put a 2x plus c, and that is a general solution. Okay? That's a general solution for that differential equation. That's why it said right here. In order to get a specific solution, as we see at the very end of this lesson, you actually need a point on the original function. Okay?
General and specific.
What?
So general, I understand.
General you have a C, specific have a number.
Yeah. If we knew a point on this original function on y, we could plug it in and then figure out what c is. That's what we're going to do at the end of the day. Okay? So, that's one term that we need to make sure we understand. Then we have this concept of the antiderivative and then this theorem. Let's look at what this is saying. Capital F of x. This is just notation that we often use for an antiderivative. Capital F of x is an antiderivative of f of x if this is true. If you take the derivative of the antiderivative, you should get the function f. Okay? That's the rule for whether or not something is the antiderivative. You could also use the notation capital F prime of x equals f of x. Okay? Now, here's this theorem that relates this all together, and we're going to prove this. Okay? Theorem 4.1 in the text says if f is an antiderivative of f on an interval I, then g is an antiderivative of f as well on the interval I, if and only if g is in the form g of x equals f of x plus c. Okay? For all x and I where c is a constant. Alright, so let's look at a proof of this, and we'll kind of explain this a little as we go as well. Alright, so to prove this, the first thing that I'm going to say is, by definition of an antiderivative, that we just saw, by definition of antiderivative, the derivative of f, capital F prime of x, equals what?
F of x.
F of x. Okay? That's the definition. Alright? Now, suppose I were to...
Wait, doesn't it equal f of x plus c?
Doesn't matter, right?
That's what we're actually proving. We're proving the plus c part in this
Alright, okay,
theorem.
sorry.
Okay? So, and I'm actually going to write my derivative notation a little bit differently here. Okay? So I'm going to use the d dx notation. Alright? Because what I also want to do then is say, okay, well, let's say I take the derivative of not just capital F of x, but capital F of x plus some constant. Okay, well, that's gonna equal capital F of x plus, or not capital, just f of x plus 0. Alright? So, since that equals f of x, since this equals f of x, what do we know about capital F of x plus c?
C is a constant.
By definition, capital F of x plus c is an antiderivative. One of the easiest proofs you'll find of f of x. Now, based on what we set up in the theorem, okay, if g of x equals capital F of x plus c, then g of x is the antiderivative, or an antiderivative of f.
I didn't quite understand the theorem.
Okay? So what this is saying here, guys, is that if I know that something is an antiderivative, then I could add any constant I want to it, and it will also be an antiderivative. Okay? And that is why, whenever we take the antiderivative with this notation right here, we write it with the plus c. Okay? So this notation right here, the antiderivative of f of x dx. Again, the antiderivative of f of x dx equals capital F of x plus c. We always put that plus c anytime we're taking the antiderivative. Okay? Back to this. Okay, this symbol right here is actually an elongated capital S. They took a capital S and then they stretched it out, because actually this has to do with sums, which we'll see in the near future. Okay, so that notation is the notation for antiderivative, and it's the, as I'm reading it, it's the antiderivative of this function f of x with respect to x. So just like on the derivative, you had d over dx, and that told you what you were taking the derivative with respect to. We have the dx here, the differential. So it's the antiderivative of f of x with respect to x is the antiderivative of f of x plus any constant. Okay?
So it is.
So yeah, so this just means capital F of x. Okay? Alright, and basically the idea is this, and we have inverse in quotes, because it's not because of the plus c, it's not exactly an inverse, but you can kind of think it along the same lines. The derivative of the integral of f of x dx is going to be f of x. Okay? Now, in this sense, it is an inverse, because even if you have that plus c, you take the derivative second, and you get 0 for that part. So it does take you right back to f of x. Okay? So that was a lot of kind of theoretical look at it and trying to understand the concept of what we're dealing with here. Alright? Let's actually look at some rules, and I think this will make it a little bit more concrete, easier to understand, okay? So, here's a whole list of integration formulas. And within a very small time frame, you should have these all memorized. Okay? Now, if you do your homework, you will have them all memorized within a very short time frame, because you're going to use them a ton. Alright? But let's highlight a couple of these. Alright?
Wait, is there a formula to go from the antiderivative to the
Well, yeah, what is it? If you go, guys, if we go from the antiderivative to the original function, what are we doing? Taking a derivative. So we already learned all those. Okay? And actually, if you think about these rules, it'll make sense. When did we get 0? When we took the derivative of a constant. When did we get a constant, k? When we took the derivative of a line, kx plus c. Here's a rule, couple of rules that carry right over. If you have a constant times a function, you can just take the integral of the function and multiply your answer by the constant at the end. Okay? If you have multiple functions added or subtracted, you can take the antiderivative of those separately. Okay?
What's the difference between the integral and the derivative?
They're opposites of each other.
Opposite.
Yeah. And they have different applications that we'll see as well. Here's the rule you guys developed. Now, there is a limitation to this rule. This does not work when n is -1. Because if I tried to use this when n was -1, 1 over x,
Zero. Undefined.
I'd get x to the 0 divided by 0, which is undefined. So we'd be in trouble. There's a different rule for that one. Okay? We'll learn that later. But then, look at the trig functions. These ones, if you know your derivatives really well,
And they're fine.
they actually make sense, okay? Derivative of cosine is sine, or the integral of cosine is sine because the derivative of sine is cosine. The derivative of cosine was negative sine, so the integral of positive sine is negative cosine. Okay? And before we look at the rest of these, let me give you a little tip to remembering your sines and cosines, okay? On the unit circle, your cosine was which coordinate?
Cosine x.
X, okay? So, positive x-axis was to the right, negative x-axis was to the left. So we have cosine and negative cosine. Your y-coordinate was your sine, so we're going to put that positive sine, negative sine. And watch this. If we rotate around this clockwise, the derivative of sine is cosine. The derivative of cosine is negative sine. Derivative of negative sine is negative cosine. Derivative of negative cosine is sine. So if we rotate around here clockwise, that gives us our derivatives. If we rotate around here
That's crazy.
counterclockwise, guess what we're doing? The antiderivative. So, the antiderivative of cosine is sine. The antiderivative of sine is negative cosine. Antiderivative of negative cosine is negative sine, and antiderivative of negative sine is cosine. And of course, all of those you'd put a plus c at the end. Alright? Well, that's a little trick to help you remember the sines and cosines. Because we mess up the negatives sometimes. So, that helps us keep it straight. Okay? If you see someone in Miss Barbeg's class, she likes to write it vertically, and so she'll show them that way. I prefer this way, but either one works. Okay? Now, the other rules for the trig functions, secant squared ought to look familiar. That was the derivative of tangent. Okay? The secant times tangent, that was the derivative of secant. Notice we don't have the integral of secant. There is a rule, but it's really complicated. I can't even remember it. Okay? So, typically we end up looking that one up if we need it. Alright? But this is what you would need to know. The integral of secant squared is tangent. Integral of secant times tangent is secant. Cosecant squared, we knew negative cosecant squared was cotangent, the derivative of cotangent. So the integral of cosecant squared is going to be negative cotangent.
Okay.
And then same thing with cosecant and cosecant times cotangent.
So if it was positive in the derivative, it is negative in the
Yeah. If you remember I said if you're taking the derivative of anything that starts with C, answer was negative. Well, for the integrals, if your answer starts with C, it should be negative. Okay? So, not quite as easy to remember, but it works.
So
Okay.
these are these the integrals?
Yeah, these are the antiderivatives. And as you'll see, integration and finding the antiderivative are kind of synonymous. When we have what's called the indefinite integral, and that's what we're doing right here.
And it's indefinite because of C, right?
Well, it's indefinite because we don't have actual numbers like an interval to integrate over. That'll give us a definite integral, which we'll talk about later. Okay? So let's run through a few examples here. Just like with derivatives, it's often helpful to rewrite these. Okay? So if I'm going to rewrite this 1 over x cubed as an x to the negative third, just like we would back with our derivatives. So I'm taking the antiderivative of x to the negative third. So that's my power rule that we came up with earlier, actually. So I'm going to take and add 1 to the exponent and divide by that new exponent. So it's x to the negative 2 over negative 2, which is 1 over 2 x squared plus c. Okay? Yeah, 1 over negative 2 x squared plus c. Okay? If I have a radical, I'm going to rewrite that as a fractional exponent. I add 1 to the exponent and divide by that new exponent, which is 3 halves. If I'm dividing by 3 halves, it's times 2/3. So it's 2/3 x to the 2/3, or x to the 3 halves, sorry, plus c. Here's where that constant multiple rule comes in. I can rewrite this if I want. I'm at least going to think this. 2 times the antiderivative of sine. And the antiderivative of sine is negative cosine. So it's 2 times the negative cosine. So negative 2 cosine x plus c. Okay?
The only derivative you carry the constant or trig.
Yeah, pull the constant along with it. Okay? Just like with the derivative. What am I taking the integral of here?
Itself, I don't know.
1.
1.
Yeah.
Remember, if we don't see anything, it must just be a 1. Okay? What's the integral of 1? X plus c. Yep. X plus c. Here I have multiple things added together. Now, we aren't going to write it out this way, but we're at least going to think of it as, okay, what's the integral of x? And what's the integral of 2? So what's the integral of x?
X,
So
one
x
half.
squared over
half.
2.
Yeah.
X squared over 2. Okay?
Mm-hmm.
And what's the integral of 2?
2x.
2x. And then we don't need to put a plus c and a plus c. You would just put one of them at the end, plus c.
Okay.
Okay? Let's try another one here. 3x to the 4th. What's the antiderivative of 3x to the 4th?
So you have 3 over 5 x
To the 5th.
It's x to the 5th,
over 5.
and it's over the 5. So 3x to the 5th over 5. We add 1 to the exponent. It's to the 5th power. We divide by the new power. Okay? How about the minus 5x squared?
We minus 5 over 3 again.
Yeah, there we go. It's over 3. X is to the 3rd power now.
Okay.
Okay? And then the plus x.
I have
X squared
Yeah, half x squared or x squared over 2. And then don't forget the plus c's. Okay.
I we don't have plus, is that wrong?
They're not totally right.
Okay.
All right, let's do a couple more of these, all right?
Wait,
When you have a monomial in the denominator, what are you allowed to do?
Break it up into two terms.
You're allowed to separate them, okay? So, by the way, there is no quotient rule or product rule for integration or antiderivatives, okay? So, but what I can do here is integral of x over radical x plus 1 over radical x dx. So this is the antiderivative of x to the 1/2 plus x to the negative 1/2. And now I'm using the power rule for both of those, okay?
So the 3 over 2 x 3 over 2
X to the 3 over 2
times 2 over 3.
times 2 over 3. Yeah, flip and multiply.
That was
Okay? And then how about the negative 1/2?
The plus a half.
Okay, so x to the positive half
Times 2.
times 2. Yeah, divided by a half is times 2. So there we have it. Okay? Ooh, what about this one?
oh,
We get to do trig. It's fun.
If it is
All right? How could I rewrite this?
sine over cosine times
It would
1
be
over
tangent,
cosine.
tangent x times secant.
Okay, yeah, look at this. Sine over cosine times 1 over cosine. Okay?
why we do that?
Why do we do that? Well, because we don't have the integral of sine over cosine squared, but check this out. I can do the integral of tangent
Alright.
times secant. What is that?
Oh, that is tangent.
No,
No, tangent would be secant squared. This is
secant.
secant.
Wait, why is it negative secant?
The c's are negative. The c's are negative. So cosecant, cotangent, cosine, those ones end up negative. Okay? So now that we have a decent understanding of how the plus c works and how these integration or these antiderivative rules work, I want to look at this idea of initial conditions in a particular solution. So we saw when we solved the differential equation, it asked for a general solution. And here we're looking at kind of the same idea. We have y is the integral or the antiderivative of 3x squared minus 1 dx. And we have this general solution for y, what y equals. Y is x cubed minus x plus c. And as we've kind of discussed, depending on what c equals, okay, that graph, which is a cubic, could be this one up here. If c was 4, it'd have a y-intercept of 4. Or if c is 3, y-intercept of 3, 2, 1. It could go through the origin. You guys get the idea. Okay? So, but what we want is we want to get this to go through a specific point. And you can see right here, we want this one here that hits the point 2, 4. So how do we do this? Okay, we call this, first of all, this point that we have is what we call an initial condition. All right, it's a condition or a point on the original function. Okay, so what we're going to do with this is we would take this general solution we have, y equals x cubed minus x plus c, and we would plug in the point 2, 4 to solve for c. So I'm going to put a 2 in for the x, and a 4 in for the y, And we have 8 minus 2 is 6. Oh, like I said, I want to put a 4 in for the y. So we have 6 plus c is 4, and that means c equals negative 2. So our particular solution is going to be y equals x cubed minus x minus 2. Okay? So just to take one from start to finish, we want a particular solution if capital F prime of x is 1 over x squared, x is greater than 0, and f of 1 equals 0. Capital F of 1 equals 0. Okay? So remember this notation, capital F prime of x, that's the same thing as saying f of x. Okay, the derivative of the antiderivative is the function. So we're going to take the antiderivative of capital F prime of x with respect to x. We're going to do that on the other side of the equation too. Antiderivative of x to the negative 2 dx, just rewriting that function. And that gives me capital F of x. And I don't need to put the plus c on both sides. I'll just put it on this right side. And that's going to be, if I add 1 to the exponent, it's x to the negative 1. And I divide by negative 1. That's going to be negative x to the negative 1 plus c. So now to find the particular solution, we plug in 1 for x. So it's negative 1 to the negative 1. And I plug in 0 for capital F of x. Negative 1 to the negative 1 power is just negative 1. So I add 1 to both sides, and c equals 1. So that means capital F of x is negative 1 over x plus 1. Okay, so that's our particular solution. Again, this was general solution. And this is the particular one that goes through this point 1, 0 that we were given.